So right now I want to take a look at how to calculate the pH of a solution that has a weak acid. Now, a weak acid is an acid that does not undergo 100% dissociation, and your general weak acid is called HA. Okay, now HA, when you put HA in water, maybe it's very, very soluble. It may be very soluble. Okay, but as a weak acid, not all the molecules that are dissolved are dissociated. Okay, that's the key. The difference between dissolved and dissociate. So imagine, just for the sake of an example, you have your weak acid HA, and maybe you've got, 10 particles of HA, and you dissolve them all into the water, and they all spread out homogeneously. Okay, and so they're all kind of doing their own thing. Individual molecules, neutral, no ions yet. 1, 2, 3, 4, 5, 6, 7, 8, 9. Maybe 1 in 10 will actually dissociate into ions like that. Okay, lots of these are all stuck together, and only 1 in 10 have dissociated. Now, to put that in a chemical equation, chemists don't like to draw stuff like this because it just takes way too long. When a chemist sees something like this, it means the same thing to them. The double arrow indicates a dynamic equilibrium. Every moment, some of these, a small number of these, are dissociating, and an equal number of these are rejoining up, and you have some type of equilibrium along with an equilibrium constant K, like we've talked about. Now, if this is an acid, this is called Ka. Okay, now Ka is normally, if it's a weak acid, reactants are favored, so it's going to be less than 1, okay, for a weak acid. And for strong acids, K would be really, really, really big. For strong acids, like hydrochloric acid. Okay, and so looking at a list of Ka values can give you an idea of the strength of an acid. Okay, the Ka value indicates the strength of the acid. Okay, so small Kas are weak acids, big Kas strong acids. Okay, the Ka value indicates the strength of an acid. Water itself can play the role of an acid. For water, the Kw is the Ka for water. Okay, because it's kind of doing this, right? Water itself is a weak acid. And so it's kind of weird to think about water molecules being dissolved in other water molecules, but that's a legitimate point of view, right? Somebody once asked, is water wet? And it absolutely is. Of course, water is wet. Can water get wet? Sure, it depends if how you look at it, okay? But water definitely can act like an acid. It can dissociate this way, and the anion is hydroxide, and so it turns out you get a neutral solution here, but it is dissociating to make H+. And so Kw is a Ka value, and it's very, very, very small, right? And it turns out that's sort of like the limit into how weak acids get in aqueous solution. Okay, so normally you can think of water as being like the weakest acid in aqueous solutions. All right, if you have a acid that's even weaker than water is, suddenly water makes the solution, becomes the dominant contributor to H+. So it's sort of like your weakest acid in an aqueous solution. You can't ever really go below that threshold in water. And later on, we're going to talk about Kb values. And so, because water is also dissociating to act like a base, and so the Kb of water is Kw. Anyway, but back to Ka, the strength of an acid. In general, acids have a larger Ka than this, even the weak ones. Okay. Water itself can play the role of an acid. According to the Bronsted-Lowry definition, acids and bases are defined by what they do. And that can change depending on the context. Water's Ka is the same as Kw, equal to 1.0 times 10 to the negative 14. That is our point of reference for acids. Okay, and pretty much, not just pretty much, all things that are considered weak acids are going to have a Ka that is basically between Kw and N1. Okay, water kind of being the lower limit. Determine the pH of 0.5 molar solution of acetic acid. Let me give you its Ka value from a reference table. It's 1.8 times 10 to the negative 5. Almost certain about that. And so, or is it 1.5 times 10 to the minus 8? I need to double check. Goodness. I'm sorry. Ka of acetic acid. At least the two significant figures. They've got 1.7 times 10 to the negative 5. I feel like I've read 1.8 times 10 to the negative 5. We're going to go with that. Okay. Yeah. So chegg.com says what I thought. Anyway, so I was right. It happens sometimes. Page width. Zoom back in. Come on. Okay. So let's determine the pH here. What we need to do is make an ice table. Okay. And so now we're back into the whole chemical equilibrium idea. You know, you guys are super excited about that. But this is actually where chemical equilibrium becomes very, very, very important. So HA, in this case, even if you don't know the formula of acetic acid, this is a good thing to know. Even if you don't know its formula, like what is acetic acid? I can't remember. Right? Maybe you do. HC2H3O2. As long as you know it's a monoprotic acid, you can write it this way. If you have reason to believe it's diprotic, you could write it H2A, okay? Or if it's triprotic, H3A, okay? But if you have reason to believe it's monoprotic or it doesn't mention that, you can just write it HA if you don't know its formula. Weak acids dissociate in water to generate H+ and A- ion. And we know the Ka for this process from a reference table. Mr. Kwood just gave it to you. 1.8 times 10 to the minus 5. Okay, so it's a weak acid. It's less than 1, and it is greater than water's Kw value. Okay, so we're going to make an ice table. The initial concentration of our weak acid is 0.5 molar. And what we do here is we imagine that there's so little H+ in this solution. There's a tiny, tiny, tiny bit from water, but this weak acid is going to give us a lot more H+. This is going to be a dominant contributor. Contributor H plus concentration. Okay, it's much, much stronger of an acid than water. Okay, so we'll talk about that later. How do you know what the dominant contributor is? It's Ka. Even though it's small, it's much bigger than water's. So effectively, we can assume that pretty much all the H plus is going to come from this when it dissociates. So the initial concentrations of these guys are 0, definitely for A minus anyway. Okay, so then we get a little change in concentration because right now Q equals 0. And it's not going to stay 0. And here we have 0.5 molar, X and X. Okay. Now, let's talk about the mass action expression. This is important. Earlier over here, I talked about these undissociated acid molecules being dissolved in water. And I've written aqueous next to this one right here, right? It says aqueous. Everything in that reaction equilibrium is aqueous. So what would the mass action expression look like for a weak acid? It would be H plus concentration times the anion concentration divided by the undissociated acid molecule concentration. We need to include the denominator for the weak acid here. Now for water, normally we don't write it that way. And in the flash drive textbook, they just said that it was really, really, really big, and so therefore is probably going to be constant anyway, so they ignored it. Okay, but that's our expression for, that's the mass action expression for your general monoprotic weak acid. So over here, what we're going to do is try to solve for X, and I need to write minus X right here. Okay, now we can do an exact solution, but in a similar way to what we did with precipitation reactions, there is a simplification we can make for this term right here. X is probably going to be really small because this is a weak acid. We're not going to get a lot of these ions over here. And so 0.5 might be a lot bigger than X. And so we're going to try it with just 0.5 right here, 0.5 molar, and plug that into the mass action expression. Okay, so what we have is 1.8 times 10 to the negative 5 equals X raised to the first power, that's this here, times X raised to the second power, divided by 0.500. That's this one right here. And this is fairly straightforward to solve. Multiply both sides by 0.5 and then take the square root. Okay, so after multiplying both sides by 0.5 and then taking the square root, we'll have X. So let me grab my calculator and type all that in. 1.8 times 10 raised to the negative 5, and we multiply both sides by 0.5. And then we take the square root of that value there. And we get 0.003. 0.003. Back to my OneNote. We found that X equals 0.003. Okay, well that's not super tiny. It's not negligible in a sense. Oh. 0.003 with 3 significant figures, or 2 significant figures from that value. Okay, now does it matter? I think it does. Okay, there's something called the 5% rule, which you should know about. In general, if this change is less than 5% of this total value up here, our approximation is valid. So 5% rule, we can use this simplification. The simplification I just showed you works if X is less than 5% of the original concentration of HA. And so HA concentration 0 signifies the initial concentration of HA. That's this one right here, 0.5 molar. And so if the change is less than 5% of this, mathematically speaking, we'll get the same answer even if we solve for the precise solution. Technically speaking, without the simplification, I really should plug in minus x right here. And if you go through and you solve the quadratic equation or whatever it is, and you end up with x, if x is less than 5% of this value up here, you'll get basically the same answer. Okay, so let's check to see, did we hit the 5% rule? Did we hit the 5% rule? And that's also the answer to this question. What's the percent dissociation? Percent dissociation is basically like, what's the concentration of H plus at equilibrium divided by the original concentration of HA times 100%. That's what we're finding. Okay, is that going to be less than 5%? Whatever it is, that'll be its percent dissociation. Okay, so this value, x, H plus ion concentration at equilibrium, divided by that initial concentration of undissociated HA times 100%. So what do we got? 0.003 molar divided by 0.5 molar times 100%. Okay, and it's 0.6% in this case. So that definitely meets the 5% rule. 0.6% is much less than 5%. And so that is also the percent dissociation. Okay. Do the same calculation for a 1 molar solution and compare the results. What happens to the percent dissociation and why? Okay, so we need to do a separate calculation, separate ice table. Oh, I haven't found the pH either. Let me go ahead and do that. How do we find pH? pH is negative logarithm base 10 logarithm of H plus concentration. So we've just done that ice table to figure out H plus concentration, which is 0.003 molar. Okay, so the negative log of 0.003. Come on, calculator. Negative base 10 log of 0.003. Three significant figures will have, two significant figures, 2 decimal places in our pH. So 2.52. 2.52 is the pH. You should be asking yourself if that's reasonable. Is this pH reasonable, 2.52? Is it reasonable? Okay, well, at least we have an acidic pH. We've got some type of weak acid, and we're in the acidic range. Remember, the acidic range is less than 7, so 2.52 somewhere in here. Oh, by the way, acetic acid is what we get in vinegar. That's what makes vinegar acidic, and that's reasonable. Cool. It's acidic, and it's not terribly low on the pH scale. Okay, so we need to do the same thing for a 1 molar solution now. That's the pH of a 0.5 molar solution. We want to find the pH of a 1 molar solution. So let me make a new page for this one. And I'll just title it pH of 1 molar HC2H3O2. Again, if you don't know the formula, you could just write HA, and that's aqueous, dissociating to give A minus and H plus, ice. Initial concentration 1, 0, and 0. Change minus x, and plus x. Go off the coefficients. It's easy to get in the habit of just writing these, but remember to look at your coefficients for the changes. This is 1 minus x at equilibrium. These guys are x and x. Ka here is H plus, A minus over HA. And the Ka value for acetic acid is 1.8 times 10 to the negative 5. And we plug in the equilibrium concentrations, x, x, and 1.00 minus x. Again, this is a weak acid, and like we did last time, we can approximate this value right here and say that's approximately going to be equal to 1, most likely. So we have x squared on the top and 1 on the bottom. Multiply both sides by 1. Doesn't change anything. X is going to be the square root out of 1.8 times 10 to the minus 5. And we get 0.004. 0.0042. Molar H plus. Okay, and how does that compare to that other solution? That was 0.0030, and now we've got a little bit more concentration, 0.0042. Not as much as you might think though, but it is more. What's the percent dissociation? That's going to be H plus concentration at equilibrium divided by the initial concentration of HA times 100%. So 0.0042 molar divided by 1, simple, times 100%. Okay, so this has 0.42% dissociation. Okay, so this is kind of strange. We see less percent dissociation in this solution. The pH, I still forgot to do this one as well. Negative base 10 logarithm of 0.0042. pH here. This will finish it up and then we'll discuss the results. Negative base 10 logarithm of 0.0042. Two significant figures in that value, so 2 decimal places in the pH. 2.38. 2.38 is the pH. Is that reasonable compared to the other one? If we have a higher concentration of our acid, we should expect this to be more acidic. Is it more acidic compared to the other pH? The first pH was 2.52. This pH is 2.38. So we've decreased on the pH scale. So let's compare our results. That's the last thing we'll do in this video. So, comparing the results, we had that had our two solutions. We had the 0.5 molar acetic acid, and we had the 1 molar acetic acid. Okay, and in the first one we saw that the pH is 2.52. This one we see that the pH is 2.38, so that's reasonable. More acidic, lower on the pH scale. In terms of percent dissociation, this one here is 0.42% dissociated. And the other one was 0.6% dissociation. So maybe not what you would have expected, but this is kind of important. In general, the higher the concentration of your weak acid, the smaller the percent of molecules that will dissociate. Okay, here we can actually see that more molecules total dissociate per liter. In terms of the molarity, it is a higher molarity. H plus is 0.0042, and that's higher concentration. Okay, the higher concentration weak acid generated a higher concentration of H plus. Okay, but the percent, this one was 0.0042 molar H plus, and this one up here was 0.003 molar H plus. Okay, so in the more concentrated weak acid, we did get more H plus, and that's why the pH is lower, but the percent is actually less than this percent. Okay, and to rationalize that, I'm going to talk about the mass action expression, and then we can be done. Okay, the mass action expression, let's see, for your weak acid, H plus A minus over HA, and that's your Ka value. And you've got your HA, aqueous, dissociating to H plus and A minus. Okay, why would you get less percent dissociation here if you have a higher concentration here? Okay, well, in terms of this expression right here, let's say you're at equilibrium, and then you dump in a bunch more HA, right? Or let's look at it a different way. Let's say you had this 1 molar stuff, and let's see, let's plug in our equilibrium concentrations here. 1 molar and okay, and so you've got a whole lot of HA that's undissociated, and only 0.42% are dissociated. So this is an exaggeration, but just to make it clear. What would happen if we diluted this by a factor of 2? So that this concentration, so we'd like double the volume by adding in some water. When we double the volume, all the concentrations in here are going to be cut in half. All concentrations are cut in half. What would that do to the mass action expression over here? Okay, if all of these are cut in half, now we're dealing with 1/2 the concentration of H plus and 1/2 the concentration of A minus over 1/2 the concentration of HA at the instant of the dilution. Okay, so now we've got a 0.5 molar HA solution, right? Okay, but how does the mass action expression compare now? Q equals what? Well, the 1/2 would factor out to 1/4 here, 1/4 H concentration times A concentration, and down here 1/2 of HA. Okay, so we've got 1/4 divided by 1/2. And so what's 1/4 divided by 1/2? It's the same as 2 divided by 4. It's 1/2. You could think of that as 1/4 times 2. So we have 1/2 H plus times A minus over HA, which is the same thing as 1/2 of Ka. So that's obviously less than K. So which direction would our equilibrium shift? If we have Q less than K, it's going to shift to the right, and that's going to generate more H plus and A minus ions. Okay, so more dissociation. It's going to shift to the right and dissociate even more. Okay, the dilution will cause even more dissociation. All right, so let's leave it there for today. Again, that's for a weak acid.